This is the last of the set of lectures on prediction, and it concerns one of the most important topics that's been developed in modern applied prediction, and that is combining predictors. So the key idea here is that you can combine classifiers by either averaging or voting. We saw that for specific types of classifiers, for example, when we bagged classification trees or when we bagged low-S regression models. But you can also average or vote across multiple different types of classification models, and this is actually quite a powerful tool. It generally can improve accuracy to very high levels using a combination of different prediction models that capture different components of the data. However, an important point to note is that combining classifiers both reduces interpretability and can increase computational time. So you have to pay attention to the trade-off of interpretability versus accuracy. That's always an important issue in prediction models. So a couple of important success stories for combining prediction models. The first is the Netflix prize. So you can see the team that won, Belcour's Pragmatic Chaos. This team was a combination of 107 predictors that were given linear weights and added up to give the overall prediction that ended up winning the prize. This idea has carried over into new prediction problems. So this is the Heritage Health Prize. These are examples from the Progress Prize 1. These are the two teams that were at the top scores at Progress Prize 1. The Market Makers team used ensembling. They added up several different models that were used together to make a better prediction. And the Mestrum team also used ensembling or used model combining. So for example, in section 5, the weights in the final blend are given in this particular analysis. So here, the different models are given different weights and added up in order to get the final prediction. If you want to learn a lot more about how each of these teams combine models, you can click on these links to go to their Progress Prize description papers. So here's the basic intuition behind why majority voting or why combining different models might be a good idea. Suppose we have 5 completely independent classifiers. In other words, these classifiers don't use the same features and predict totally independently on the dataset. Suppose that the accuracy of each classifier was 70%. Then in order for a majority vote classifier to be correct, either 3, 4, or 5 of the classifiers would have to vote for the correct answer. So there are actually 5 choose 2, which is equal to 10 different ways that 3 classifiers can vote for the right answer and 2 classifiers can vote for the wrong answer. Each of those occurs with probability 0.7 to the 3. That's 70% of the time they're right, and there are 3 of them that are right, and 30% of the time they're wrong, and there are 2 of them that are wrong. Then there's 5 choose 4, or equal to 5 different ways that 4 classifiers could be right and 1 classifier could be wrong. And in this case, there's 0.7, which is the accuracy of the correct classifiers raised to the 4 because there are 4 correct classifiers, and 0.3 raised to this should be a 1 here, ways that the classifier could be wrong. Then there's 5 choose 5, exactly one way that all 5 classifiers could be right. That's if they all correctly classify. And that happens 0.7 to the 5% of the time. If you add all of these up, the 3 different ways that a majority vote would vote the right way, you get 83.7% majority vote accuracy, which is higher than the accuracy of any of the individual classifiers. If you had 101 independent classifiers, you would actually get 99.9% majority vote accuracy if they were all independent and you followed this same calculation. So combining classifiers, especially if they're independent or capture different parts of the information, can dramatically improve the prediction accuracy that you get. So there are different approaches for combining classifiers. You can talk about bagging, which you can see in the previous lecture, boosting, which is another very cool and type of improvement over standard prediction models. I'm not going to have time to talk about that in this class, but you can see the Wikipedia page and references therein for a lot more information about boosting. Or you could do combining different classifiers either in a weighted or unweighted fashion simply by averaging them or by taking majority votes. So here's what I'm going to do. I'm going to show you an example of how we could actually combine models to get a better accuracy. So for this, I'm going to use a simulated data set. I'm loading this Medley package, which you can actually get from GitHub. So if you don't have DevTools, you'll need to install it. Then you can load the DevTools package and install the Medley package from GitHub. Once you have the Medley package, you'll be able to calculate the RMSE values on the following slides. So here I'm going to set the seed and generate some Y values. And then these are the values that I'm going to try to predict. Then I generate a bunch of different X values that have relationships to the Y values, but all of them have different potentially strange relationships. For example, X1 is all the cases where Y is greater than 0, X2 is Y times a different normal random variable, and so forth. So then what I do is I create a data set that has the Y values and all of these different X values that I've created that I can be used to predict the Y values. I then take a subsample of this data set of size 500 and call it the training set, and the remaining values I'll call the test set. This way I can build values on the training data and test them on the testing data and compare different prediction models. So the first thing that I could do is I could fit a linear model that relates the Y variable to all of the remaining variables. So again, that's Y tilde, and then I use this dot to represent all the remaining variables in the data frame trained data. I can then calculate the predicted values using the predict function on the test data set, and I can calculate the RMSE, or root mean squared error, for comparing the values that I predict to the values that actually occur in the test data set. The root mean squared error is equal to the sum of the difference between the predicted value and the observed value squared, and once I've summed up all those values, I take the square root. The smaller the value of the RMSE, the better the predictor. So in this case, I get 1.294 as the value of my RMSE. I can then use a tree model from the tree package to do the same prediction. So again, I relate Y to all the remaining variables in the training data, and then I calculate the RMSE using the prediction from that data on the test data set. And I get another prediction error that's 1.299. Just for good measure, I'm also going to take a random sample of the data set using sampling with replacement. And so I get a similar bootstrap sample and a bootstrap tree too. I can then combine the two models that I get, the prediction from the linear model and the prediction from the first tree, and I can average them together by adding them and dividing by 2, and then calculate their RMSE from this combined model in the test data set. And it turns out that reduces my RMSE by in the hundredths place. I can also combine the three models, the original linear model, the first tree, and the bootstrap tree, and do the same thing with RMSE, and I in fact get even a more dramatic reduction in the RMSE by combining the three models together and averaging them. You can actually use the Medley package to do this in an automated way. The Medley package was designed by Martin O'Leary, who has been very successful in Kaggle competitions through the Kaggle website. You again need to install the Medley package through GitHub. Then I'm going to use two libraries here, the E1071 library, which is kind of a weird name library that allows you to use support vector machines, which is another type of prediction model that I'm not going to be talking about in this class, but is another way that we can predict, and it'll be useful when we're using this Medley model to combine with random forests. So again, I'm going to generate some training data. Here in this case, I'm going to set the training data to be all of the different variables in the training data set minus the Y variables. Then I'm going to set the Y values to be the Y values in the training data set. I'm also going to generate the new X values in this first slide, which are the values of all the X variables in the test data set. So all the columns minus the Y values in the test data. I can then use the create Medley function, and I pass it X, the matrix of predictors, Y, the outcome, and then whatever error function I'm going to be looking at. In this case, I pass it the RMSE function because the root mean square error is what I'm looking to minimize. Then what I can do is I can use the add Medley function to add different models to our combined model. So in this case, I take our Medley object and I'm going to add support vector machine models. So SVM is a function that appears in that library E1071, and so this SVM function is a different way of predicting, just like random forest, LM, or tree are ways of predicting. I can then pass it different values of the tuning parameters for that particular prediction model. In other words, these are parameters that get passed to the SVM model that are different each time, that give slightly different prediction errors. So I do this over 10 different values of these different parameters to get 10 different prediction models, which I've included in my combined model. I can then also try different values of random forests. So in this case, I'm setting a parameter here, mtry. This is the number of variables to try at each particular node. I try it with 1 and with 2. So this adds 2 different random forest models to my combined Medley model. I can then use prune Medley to pick only the top 80% of the models. So this actually removes all the models that are the least accurate from this particular combined model. I can then look at the RMSE of the prediction that I get from my combined models applied to the new X values with respect to what the actual observed outcome is, and the outcome in this case is Y. In this case, I get a prediction error that's 0.4953, which is substantially smaller than any of the errors that I got by combining only a small number of models. This Medley package is somewhat sparsely documented, but is a very nice way to combine multiple models quickly and in an efficient way. So some notes and further resources. Even simple blending can be useful. Even simple combinations of models, even if it's just a basic linear combination with simple weights or even averaging, can be very useful in improving accuracy. In binary or multi-class data, the most common approach is to do majority vote rather than taking the average, because you have factors, levels that don't necessarily average out like continuous values. It does make models hard to interpret. An important consideration is that even though the Netflix prize was won by that blended model, it was not actually implemented by Netflix because it was too computationally intensive to provide recommendations for a large number of people. Some further resources here are on Bayesian model averaging, which is an approach for combining linear models using a Bayesian framework. Some information on the Heritage Health Prize milestone winners that includes descriptions of how people have averaged a large number of models to win these complicated prizes, and a similar description of the model that was used for the Netflix winning prize.